So the next type of variation of the graph we're going to look at is when it's to the power of something. We're basically only going to look at powers where they're integers, and positive integers for that matter. I mean, you could do negative integers, I suppose, because you would go positive integer first and then do the reciprocal of that graph. Fractional ones, well, we'll have a look later on how we deal with the roots. So at this stage, we're just talking about integers that are positive. So the first thing we notice, if we have a look at the derivative of function x to the power of n, so bring down the power, lower the power, diff the inside. So that tells me stationary points remain stationary points. Again, the y value might change, but at the same x, because the original graph, f dash x will equal 0. Well, on my new graph, it's multiplied by f dash x, so it'll still be 0. So we're still going to get stationary points where there were originally stationary points. So those x values, let's put those in. So let's do squared, okay? We had a stationary point, but we're squaring it, so this y value, it's above 1. Square a number bigger than 1, it's going to get bigger, so I know it moves up. Now this one here, we've got to be careful, because when we square a negative number, it becomes positive. The magnitude of the original graph is smaller than 1. So when you square a number smaller than 1, it gets smaller, so it should go closer to the x-axis than the original one. Okay. But also, have a look at the derivative again. It's function x is inside the parentheses, or the brackets. So that means anywhere there was originally an x-intercept, it must become a stationary point. Because on the original graph, function x was equal to 0. It was an x-intercept. But our derivative of our new graph is times function x to the power of something. So again, it must equal 0. So all of those x-intercepts will become stationary points. Now the y value will still be 0, because you square 0, you'll get 0. So we know there's going to be stationary points there. Whether they're turning points or maybe horizontal points of inflection depends on how the graph has to travel. Now the vertical asymptote, that's going to remain there, because if it didn't exist in the original graph, it can't exist in the new graph. My horizontal asymptote, well, it's, you'll notice, less than 1. So therefore, when I square it, it'll get smaller. So it goes closer to the x-axis. Again, 1 being an important point, because we know when you square 1, you'll get 1. So we know that point will remain. But if the magnitude of it is bigger than 1, then the new graph will be above the old graph, because the y value must get bigger. But if the magnitude of the original graph is less than 1, then the new graph must be below the old graph. So what do we do from here? Over here on the left-hand side, well, actually, let's plot in 1 first. That's probably a good idea, because we know 1 squared is 1. So let's plot those in. So all of those points will remain. Negative 1 over here, well, that'll become positive 1 when we square it. So it'll go up there. So I've got to pass through all those points. I know my asymptotes. Starting from the left, the blue curve is less than 1. So I know the new curve will be below it. So it'll go below the curve, it'll come through this point and then go above the curve. Like so. And we'll do that for each of the sections. We know we've got those turning points, because they had to be stationary points on the x-axis. And I've got to bend towards the asymptote. Let me get rid of, well, before I get rid of, you'll notice things like, well, it's a bit hard with the negative because the original graph's down here. But when I have a look at the positives, you'll notice here we go under the curve, we hit 1 above the curve, we hit 1 below the curve, and then here under the curve. So getting rid of all the construction there, that's what function x squared would look like. Okay? Now, if n is even, like the one we just looked at, because squared being even, of course, then we know we're always going to be positive. But if it's odd, it's going to keep the same sign. So let's have a look, same curve, but this time we'll cube it. We'll cube it. Stationary points will still remain, and those x-intercepts will become stationary points, but now they will become horizontal points of inflection, because it's going to look like the cubic rather than the square of the last one. Let's draw in horizontal asymptote. Again, if you cube it, it's going to get smaller. Vertical asymptote will remain. What's the next bit to do? Oh, well, 1 cubed is 1. In this case, -1 cubed is -1. Once again, I'll go below, above, and so on. But this time, when I go through these x-intercepts, it'll be a horizontal point of inflection, which I will try and attempt to do. Oh, a bit dodgy, but okay. There's my attempt at getting those horizontal points of inflection there. Not easy in PowerPoint, but we get the idea of what it's trying to do. Let's, oh, it looks even worse when I get rid of the construction, doesn't it? But I suppose the key thing we're trying to say here is it doesn't just cut it like a graph. It is a graph. It doesn't just cut it like a straight line, but it comes through as like the cubic because it's power of 3 and so on. I don't know that I've ever seen a question which says power 4, 5 and so on. They usually just say square or cube, but I mean, if it's even, it'll be like our first one. If it's odd, it'll be like our second one. Okay.